started, we are into linear momentum balance, we are into the differential form of linear momentum balance. We derived the left hand side, the right hand side looked at the gravity, the body force, and for understanding the surface forces on the right hand side, we have taken a diversion to solid mechanics. That is one main reason is to understand better, and you will realize that as we go along, and also to look at the analogy between solid and fluid mechanics. So, now we are the first time using this arrow mark. We are taking a diversion going to solid mechanics. In that we are going to discuss about stress, that is why that is highlighted. Okay. So, in terms of our this journey to the Navier-Stokes, we started with the Newton's second law of motion, applied the Reynolds transport theorem and derived the integral form, applied that integral linear momentum balance for a small control volume, derived the differential form of linear momentum balance, not the in entirety, but the left hand side and also the gravity on the right hand side. Now, we have surface forces to be included, and that is why we are entering this domain, this dashed box named as 1. In that we are going to look at this particular section. Just want to tell you that orange represents solid, that is the legend used here, and blue represents fluid. So, now if you look at each section here, 1, 2 and 3, each has both solid and fluids, that is why we say we are going to study both parallelly. So, now we are going to look at this orange color box, which tells about stress vector and in terms of stress tensor. What is that, you will understand as we go along. Okay. So, solid mechanics, the first visit, and the first highlighted one shows the title of the first visit, internal forces and stress, and whatever is not highlighted are the topics for the subsequent visits. Okay. So, we are going to discuss about internal forces and stress, and now this is outline for internal forces and stress. So, I think you should have very clear idea where we are in. Okay. We are somewhere deep inside. We are deriving linear momentum balance, in that differential form, in that the right hand side the surface force, and to understand that we come to solid mechanics. In that there are 3 sections, and it is outline for the first section. Okay. Internal forces and stress, that is the title. We are going to discuss about stress as a vector, stress as a tensor, and what is the relationship between the stress vector and stress tensor, and properties of stress tensor. Okay. As we go along, we will understand these terminologies. Okay. Okay. Now, where do we start? We start distinguishing between rigid versus deformable bodies. Mechanics of rigid bodies, if you have taken a first year course in engineering mechanics, you would have studied mechanics of rigid bodies under static condition and dynamic condition. Okay. Usually the title of the book or the course is engineering mechanics. Okay. Now, in as the name suggests, rigid body, the assumption in this course, throughout the course, in fact throughout the course, is that the body which you are considering is rigid. What does it mean? We will take an example like this, an object, and then how much ever force you apply, of course you can divide by area, express as normalized force. How much ever force you apply, there is no change in shape, there is no change in volume, no change in size as well. Okay. So, this which means an assumption. Okay. How do you more formally say, if you mark 2 points on the object, there is no change in the distance between the 2 particles. Now, I should emphasize that when I say particles, these are solid particles. We have come across several times fluid particles. Now, move to solid mechanics. So, these are solid particles. So, the entire course is based on assumption that the body is rigid, which means that if you apply whatever amount of force, absolutely there is no change in shape or size or volume, whatever happens. Okay. Now, of course, in reality that's not going to happen, so that's why it's an assumption. Okay. Now, what is that we should discuss? We should discuss mechanics of deformable bodies. Okay. And what are the titles of the books which deal with the mechanics of deformable bodies? Either they are called as mechanics of materials or strength of materials. Accordingly, the course would also be named as mechanics of materials and strength of materials. Okay. Now, why should we discuss deformable bodies? Now, remember, we have come to solid mechanics not to really understand solid mechanics as a whole subject. The whole idea is to understand fluid mechanics and take some part of solid mechanics to understand fluid mechanics. So, if we are restricting ourselves to rigid body mechanics, that is not going to help us, because fluids are deformable, and that is why we discuss solid mechanics, deformable solid mechanics. Okay. So, and of course, that is a reality. What does it mean? If you apply a very large force, there is some small change in dimension, some change in, let us say, shape or volume, and but of course that is not visible to your naked eye. You will see later on that those changes are order of 10 power minus 6. Even if you apply megapascal of let us say force per area, the change in dimension would hardly be something like 10 power minus 6 meter. So, you may not be able to visually see, but they do undergo a change in shape, change in size or volume, etc. So, that is a reality, and that is why we discuss mechanics of deformable bodies. So, now in terms of a more formal definition, if you mark 2 points, the distance between them changes. Okay. Of course, we will discuss more about this in detail, what do you mean by distance between these two particles changes, etc. But right now, as a very quick introduction, if you mark 2 points subject to this to very large force per unit area, then there is a change in the distance between them. Okay. If there is no change in the distance between them, it is behaving as a rigid body. Okay. But there will be a very small change. It is for us to consider that or not. You are not consider that when you discuss mechanics of rigid bodies. Okay. Solids, when I say solids, deformable solids, and fluids are deformable. Okay. That is why we are discussing. Okay. Now, when I say fluids, of course gases and liquids are both included. Okay. And now we are going to discuss about internal stresses and deformation. When you discuss rigid body, you need not discuss about internal stresses and deformation, but when you are discussing deformable bodies, internal stresses are set up, the body undergoes deformation, and once again later on we will discuss formally what is deformation. Right now let us understand the usual way. So, we discuss about internal stress and deformation, and this of course the first part of solid mechanics we discuss internal stresses. Okay. That is the scope of what we are discussing. Now, if we had an introduction to deformable solid mechanics, this kind of diagram should be kind of familiar. As introductory part, what is shown here is a square rod subjected to axial loads. Axial loads are something perpendicular to the cross section. Okay. Now, if you make a cross section as it is shown here, okay, and then of course the internal forces are set up in response to the external load, okay, what you apply, and if you take a cross section, the internal forces will be perpendicular to the cross section, and hence you can evaluate a normal stress. So, let us say you take the resultant of the forces distributed across the cross section, you take a resultant, take the magnitude, let us say that is P, divide by the area over which it acts, you get the normal stress. Okay. And these are just average values over the entire section. Okay. What we are interested is more than this, we are interested in the variation of stress point by point, and of course respect to angle as well, but these are very introductory definition of an introductory way of looking at normal stress by dividing the magnitude of the resultant force divided by the area. And because the forces are perpendicular to the cross section, they are called normal stress. Okay. You have a plane and the force is perpendicular to the cross section and hence called as normal stress. Okay. Now let us look at another way of another configuration shown on the right hand side. So, here again you have a, let us say a square rod, but now you are applying transverse forces as shown here. Okay. And once again if you make a section between the 2 points over which the forces are applied, the loads are applied, then you will have a section over which there is a once again a distribution of forces, and then you take a resultant, and then if you take the average of that force, and now that force acts tangentially on the surface. Okay. So let us take this one, and then that force acts tangential to the surface, and hence it is named as shear stress. So how do you once again evaluate that? You take the magnitude of the resultant force, if you denote it as P, and then area, now area becomes the tangential area, and if you divide you get the average shear stress. Once again this is the definition of average shear stress. We are interested in a more detailed description of stress in terms of at every location, in terms of with respect to different angles of the plane, etc. Okay. These are well defined planes, one is let us say horizontal, one is vertical, but now we are more interested in stress on any plane, etc. Okay. So this is just to give an introduction to what you would have come across as normal stress and then shear stress. Normal stress acts perpendicular to the plane, shear stress acts tangential to the plane. Okay. Now let us move on to a more detailed description of stress. Okay. Now we are going to discuss about internal forces. What is shown on the left hand side is a body subjected to external forces. Let us say a body like this subject to, let us say some, we have to look at reaction forces, etc. So let us say it is subjected to external forces, and then since we are interested in internal forces, we make a section at a particular angle. Okay. At a particular point inside the object we make a plane, and now because there are different angles, same point, but different angles of the planes are possible, which means that you will have to identify that plane. So as usual we will use the unit normal drawn outside our region of interest to help identify the plane, the angle of the plane. Okay. That is what we have done earlier also. For control volume we have taken an outward normal to identify the direction of, for example, if this is the surface, then we take this as outward normal. So this helps identify the direction of the surface. But now what we have is we have taken a object and made a section, and that we have a point, at that point I pass a plane, and that plane, the orientation of that plane is identified using the outward drawn normal vector. Okay. Now what do? I section the solid, and we are now going to discuss the bottom portion of the solid. Okay. Now this is one reason why we have come to solid mechanics. If I say that imagine a fluid, you can make a section, imagine a plane there, little more difficult there, but now it becomes very easy. I can even show you that have a solid, I make a section. That is one reason we have come to solid mechanics, to understand about internal stresses. Okay. In terms of principles, analogously most of the concepts can be carried out to fluid mechanics. Okay, that we will discuss later. Now we will say the entire object is under equilibrium, okay, the left hand side entire object. If you want to represent in terms of vectorial notation, this sigma f represents all the external forces acting on the object is equal to vectorial 0. Okay, so vectorial equation. So if you sum all the forces, it should be 0 because we are taking the body to be under equilibrium. Now the whole body is under equilibrium, every point in the object is also under equilibrium. So in the right hand side, when you make a section and analyze, let us say the lower part, that is also in equilibrium, but only difference is that in addition to the external forces, you have a distribution of here internal forces. Why is that? This top portion, whatever it exerted on the bottom portion, those forces are here distributed over the entire area. So you have to take that forces which are the internal forces, also into account in writing the equilibrium relationship. Okay. Now, we are not going to consider the distribution, we are going to just now consider the represent that as a resultant force, which is denoted as F star. Okay. Of course, the normal to the plane is shown here, and F star can be at any angle to the normal to the plane. So, now if you want to express the condition for equilibrium, sum of all the external forces, these external forces, okay, plus this resultant force should be equal to 0. What is this condition? This is the equilibrium condition for this lower portion of the object. Difference between this expression and this expression is that because we are writing equilibrium relationship for the entire object, you do not have any internal forces, or in this case internal forces. Because we are analyzing a part of it, we are accounting for the forces exerted by the upper portion on the lower portion and representing it as though it is distributed over the entire area, we are representing it as a one resultant force F star. Okay. I like to mention that in the analysis what we are discussing, going to discuss, we are not going to discuss about moments. Okay. If we were very formally discussing, we will have to discuss moments as well, but in terms of the concepts which we want to take over and understand, discussion of moments is not required, since that will add to a little more difficulty. We are not discussing about moments, okay, but otherwise formally I should write a moment balance, etc. In henceforth also we will not discuss about moment or moment balance. Okay. Okay. Now, in terms of a definition of stress vector, etc., it is not required. So, let us proceed. We have considered a body, equilibrium for the entire body, made a section at a particular point of a plane at a particular angle represented by n vector, and considered that also under equilibrium represented by this relationship. Okay. Now, this diagram is same as what was shown earlier on the right hand side. Now, if you are considering the, let us say we have the body, we consider the lower portion. Now, if you are considering the top portion, what happens? The lower portion exerts a force on the surface on the top portion. So, now because at the same point we are on either side of the same surface, so based on Newton's third law, both should be same. That is what is shown here. What is shown here is this, the lower portion the same as what is shown here, and then the top portion. What we considered is this resultant force, which is the effect of the top portion on the bottom portion. Now, what is this minus F star effect, the force, resultant force because of the bottom portion on the top portion, and remember they are the same surface, one is on this side, one is on the other side. That is also clearly indicated here by using the normal, this n vector, this is minus n vector. So, F star is equal to minus F star. If you look at the bottom portion, it is F star, which is the force because of the top portion. Look at the top portion, minus F star is because of the bottom portion. Just to tell you that on either side the forces are of equal magnitude, opposite direction. Okay. So, now let us proceed further. What we will do now is, we have got a resultant force, we will resolve that in the resultant internal resultant force. Okay. Now, if you want to resolve, then you should choose a coordinate axis, you should choose directions. Now, we will choose a set of 3 directions which are attached to the surface. What do you mean attached to the surface? I take one direction which is normal to the plane. I have a plane and take a direction which is normal to the plane. Okay. Let us assume this is an internal surface, though it is as external. This is a plane, I take a direction which is normal to the plane, and then I take 2 directions which are on the surface or tangential to the plane. Now, the question arises, why should I take 2 directions on the surface? The reason is that, let us say you resolve one normal to the plane and one on the surface, that again once again can be resolved into 2 further components. That is why we take 2 directions on the surface of the plane and then of course one normal to the plane. So, we have chosen 3 mutually perpendicular directions. Why are we choosing? We are going to resolve the resultant force along these 3 mutually perpendicular directions, because they are normal to the plane and 2 on the surface of the plane. That is why I say this coordinate axis is, it goes along with the plane. It is not our usual x, y, z coordinate axis, we will come to that shortly, but now as of now this coordinate system is associated with the surface, Okay. Now, we will resolve our resultant force along these three mutually perpendicular directions, and that is what is shown in the right hand side. The force F star, we are resolving. So how should you look at it? We are very familiar with the velocity vector. We know Vx, Vy, Vz, which means that velocity has been resolved along x, y, z axis. Instead of that, here we have a resultant, instead of velocity vector we have f star vector. Instead of x, y, z, here we have denoted the coordinate axis as n, and because they are on the surface, it is denoted as S1 and S2. Okay. So, instead of x, y, z, we have n vector, S1 vector, S2 vector. So, now we are resolving this f star along n vector, which I denote as Fn, along S1, which is Fs1, and then similarly along S2, which is Fs2. So, and that is what is shown here. The F star vector has been resolved along n direction, S1 direction, S2 direction. What are the components? F1, Fs1, Fs2. Only step which are done here, or two things we have done in this slide. First is introduce a coordinate system associated with the plane. One is normal to the plane and two along the surface of the plane, normal direction, tangential directions, and then the resultant force has been resolved along the normal direction and the two tangential directions. We have given notations for them as well. So, now let us proceed further. We said we are interested in the stress etc. at a point, but now we have taken a plane and then defined a resultant vector over the entire plane. So, as we have done for, remember, for control volume, we took a control volume and then shrink it to a point, so that we get a point form of differential balance of mass and then left hand side of momentum balance etc. Similarly, what we will do now here, we take a small area, we are not taking a volume, very obvious reason, because these are surface forces. So, we are interested in a small area and look at what is happening that area and shrink it to a point, so that we can look at the variation of the surface force or the stress over the entire area. So, we take a small incremental area and the direction of that is n vector. So, obviously, it can vary from point to point, taking a small area delta A, and then the normal to that area is delta n. So, now because the area is incremental, the force is also denoted by incremental delta F star. What is that we are taking? We have F star, which is an average over the entire area, taking a small area. So, the incremental of the resultant force is denoted as delta F star. Now, this is where we are going to define what is a stress vector. Okay, what is stress vector? Also called as traction vector. What do? You divide this delta F star by delta A, and then this take the limit of delta A tending to 0. The physical significance, as we have done exactly earlier, writing the balance for a small volume and then shrinking to the volume to a point, so that you get differentially. So, remember, all the terms in our equation should be point values. Remember, we are discussing, we are going to go back to the fluid mechanics linear momentum balance equation differential form. On the right hand side, the point value of surface force, which means that my definition should be applicable at a point and should be valid at a point. That is why I make this delta A tending to 0, so that I get stress vector. Why is a vector? Because incremental force, which is a vector, divided by area gives you a stress vector acting on a acting at a point on a plane whose direction is n denoted by n. What is Tn? Tn is a stress vector denoted by T vector, and then the subscript n tells you that this stress vector acts on a plane whose normal is n vector. Okay. So, when you imagine this, you should imagine a very small plane, just like we said you will imagine a small control volume. Here again you should imagine a very small area, because that can vary from point to point. Imagine a small area, very small area, because it tends to 0, and what is the stress vector acting on that plane? We say the plane is denoted by the normal and that small point. Okay. So, the first notation we introduced now in terms of stress vector, we will use this very frequently as we go along, also called as traction vector. So, you can come across both these terminologies, we will mostly use the terminology stress vector. Okay. Maybe stress vector we are going to discuss later on stress tensor, and so you will have to be really, if you just tell stress that does not give the complete information, you should clearly mention whether it is stress vector or stress tensor, but if you mention just traction, it is all automatically indicated that it is a vector. Okay. That is a small distinction between using stress vector as a terminology and traction vector as a terminology. You just leave it as stress, it is incomplete, it could be vector, it could be tensor, but if you say traction, invariably it is a vector, traction vector, but we will use the terminology stress vector. Okay. Okay, this right hand side we will come across this in the next slide as well. Okay. So, I will discuss then. So, we have defined the stress vector, and that is what is shown here, that is what is shown here.